Brave is a great Moana.
Moana is really good.
Anything that I
All right.
think.
So a quick example of 23. You're gonna find these ones hopefully like pretty easy, because this says if you're given, notice you're not given the actual function, you're just given this. By the way, what did they just tell you about the function with that statement? A point, exactly. They gave you a point on the function. The point that says the point 314 lives on the graph. Okay, so I might even sketch a little graph of what I'm doing as I do it. 314 lives on the graph. That's all I know so far. They also told us that f prime of 3 is 20. So suppose that's all you knew about the function. Now, that's telling us that it's very steep at that value. So this function is, it could be a parabola, it could be a cubic, who knows, but all we know for sure is that it's very steep at 3. So right here, I know that the slope is 20. All right, before I move on, are there any questions on those two things?
No,
Good.
man.
Very good. So what is the best estimate we can get for f of 3.1? What'd you say? 16. Okay, very good. If you do that in your head, that's awesome. If not, no biggie. So someone who did it in their head, what's the, right, you said, okay. Give us a brief overview of the logic. How do you know it's
So if the
16?
slope is 20, then it's 20 over 1, and then it's asking for 0.1 over, so divided by 10.
Very good. Okay. So you can reason these ones out, like just think about, well, yeah, the slope is 20. So if I'm only going over a tenth, if my run is a tenth, then my rise would have to be 2. So let's say you're like, it's a lot to do mentally. Well, and also some of these will be a little bit more challenging to do in your head. So the slower way, the more sort of like methodical way is just to write the equation of this tangent line. Say, okay, I'm doing a tangent line approximation. So I'm going to say, all right, in the neighborhood, so near 3, I can approximate my function as y minus 14 equals the slope times x minus 3. And then all I got to do is plug in 3.1 for my x value to get the y value. So my y value would be 20 times 0.1 plus the 14, which of course would give me 16. So the answer is 16. Does that all make sense?
Mm-hmm.
So there you go. So those should be fairly straightforward. 26 and 27 are just worded a little bit differently. They're just asking you to approximate the x-intercept or the y-intercept of some function based on the same information, but it's the exact same approach. You can write the tangent line formula, and then to get the y-intercept, you'd just be plugging in 0 for x, and to get the x-intercept, you'd just be plugging in 0 for y. Yeah, right?
Is that 26 a typo, like the derivative of h?
It is. Thank you. Yes, thank you. Yeah, 26. Typo on 26. It's supposed to just make them all k's.
Okay.
Okay.
I get it.
I hope.
That's good.
And then, yeah, same thing. 25 is basically just asking, what x value would make the y value 0. So, same idea. Okay, so mean value theorem. Unless there's any questions that you guys want to address before we move on.
You're welcome for that weird ass laugh.
What?
I said you're welcome for that weird laugh. It was very strange.
Thank you very much.
Thank you.
So,
Okay.
I've
been having less
real quick, let me make a note to myself to fix that typo.
feeling less and less about this. Yes, so I realized I said I think Gary was about the plate instead of place, and I was laughing at myself. Friday, yes. My house, your house.
Okay. Mean value theorem says.
This solves that.
Mean value theorem.
Yes.
These markers are killing me. How about this one? Should I start throwing them away as soon as they start doing this? I feel bad. It's like they still got a little bit of life in them.
You
Rafe says
draw
yes.
an elaborate photo, so then you know that they have
They're not
a
bad.
good last.
Pull the plug.
Ooh, that one
Oh my
is
God. That's a good one.
stonky.
This one's looking good.
Stonky? I don't know. I couldn't think of a good Is that a description?
That's crisp.
Oh, I should go back and put them in the box in the closet. Yeah, that's a good idea. Yeah.
That actually would be very funny.
That way, you just literally-
I think you should. No, I think you should trade them out with all of Mrs. Lucas's.
Thanks.
That would be so.
So
No, I'm just kidding. I
Marcus,
love
though.
Miss Lucas, and
But she would never use them. She uses only usually on a board.
the mean value theorem is it's actually a very intuitive theorem. So it says that let's say you have 2 points on a graph. Okay. Now it says that the point 3, 6 lives on our graph. So I'm not going to draw it really to scale.
Lame.
Me and Jesse.
That's all we know so far is that some function contains those 2 points. I need to look one more time, sorry.
You do a little peepsy.
Oh man, I love this class.
Okay.
So they
I just want to make sure I had the order correct. So the first thing just says, what's the average rate of change of the function? So the average rate of change is just rise over runs, it's the slope. So you'd go 8 minus 6 divided by 7 minus 3, which of course is 1/2. Okay, nothing crazy there. And then it says, I already forgot what it said. Oh, what's wrong with me?
I call
Okay, sorry. Sketch a possible graph. So what's a possible graph where there would have to be some value c in the interval 3, 7 such that f prime of c equals 1/2. So we already ramped up just reading that could be a little challenging, right?
Yes.
What's a possible view of this graph? I'm going to draw one for you. Okay, there you go. Now, what am I talking about? Notice I just drew a nicely behaved graph. Nice, nothing pointy, no jumps, no asymptotes, right? So what that thing says is, if I draw my graph in a nicely behaved way, then there's guaranteed to be, it's right around here, some x value named c. Okay, so I'd say there exists some x value named c such that the derivative at c is equal to 1/2. So I'd like to take our time getting through these statements because they're not easy. They're difficult to parse and figure out what they mean. Also, for you, the flex people in here, if you want to flex your special symbols, you could write this as there exists a c in the interval between 3 and 7 such that f prime of c is 1/2.
Oh yeah.
So that's pretty savage.
Fancy.
Yeah, that's pretty lit, right? That symbol means you don't have to know this for this class. This is for funsies. This is there exists a c inside the interval, or c, which is an element of the interval from 3 to 7, such that the derivative at c is 1/2.
I love it. I can't wait for even more of these.
You don't need the fancy symbols though. This, if you can understand the English language and you understand what derivatives are, you're capable of understanding the sentence. So I'll give you a simple example. What if this was a time axis? Okay, this is a snail. For a snail, this could be his time in hours, and this could be his position in miles. So what was his average velocity between time 3 and 7? 1/2 miles per hour. Now, does it stand to reason, just logically, that if his average speed was 1/2 of a mile per hour, that at some point in his journey, he was traveling exactly 1/2 a mile per hour? Okay? I'll give you a simpler example. Maybe that's not a snail. This might be more salient to you since you drive cars. Let's say between time 1 hour and time 4 hours, you went from a position of 30 miles and you hit, sorry, 200. I want to pick an easier number. Sorry, so 90.
90?
That's a
So-
good jump.
And so your graph, and suppose you didn't teleport or anything crazy. Well, does it stand to reason that if you went 60 miles over a 3-hour period, then there must have been some moment in time where your speedometer was reading exactly 20 miles per hour? You're in a school zone. It's a big school.
I don't know. I said, hold on,
That is a huge school.
Maybe you're in a residential area for a long time.
I still got
Like 30.
No, actually, the explanation is you're ahead of me on the road to pretty much anywhere I want to go, especially Big Mountain or Glacier National Park.
Oh, yeah.
You detected that Jake Hall is in the car behind you, and now you have to drive half the speed limit.
I saw a
Okay.
deer. Mr. Hall. I saw a deer. I just stopped.
Wait, no, I'm confused. You said it would make sense if you were going 20 miles per hour.
So
right?
what I said is, so look at this graph here.
Yeah.
All right, everyone, quiet down. So do you agree that like right here, I'm going faster than 20?
Yes.
Because this slope is 20.
Okay.
So I was going faster than 20, then a little bit slower, but at a certain point, I must reach some moment in time where my speedometer is reading 20 miles per hour.
No, I get you now because you're talking about slope. You're saying that, but I thought you were talking about like miles, and that just didn't make sense to me, like, because you never went below 30. That was
Right. That you're obviously making a good point here. You guys are, Jordan, you're missing it here. So, George.
I was talking
Just call him Jordan.
Okay. I said George. There's two things here happening here. The mean value theorem is going to be about how if this is a nicely behaved curve, then there must be some point where the slope, the instantaneous rate of change, the derivative, is equal to the average rate of change. There's also something called the intermediate value theorem, which is simpler, which is if I go from the 30-mile marker to the 90-mile marker, was there some point where I passed the 50-mile marker? Like, yeah, that's the most obvious one is there must have been some point where I passed, you pick any y value between 30 and 90, and if the function's continuous, you have to pass through that point. Does that make sense?
Yeah.
That's much more elementary, so that's giving it a fancy
Dear
name.
Watson.
What?
We both did elementary, dear Watson, at the same time. It was very funny.
It was very funny.
Anyway, so the intermediate value theorem would say that there must be some point on this curve whose y value is 7. Okay, all right. So the way I've drawn this is there must exist some value c. Now again, c is just an x value, such that f prime of c is 1/2. Yeah, that's another way to say it. Yeah, you could certainly phrase this question as, phrase the theorem as there must exist a point on the curve whose tangent line has a slope of 1/2. Is that what you're thinking? Yeah, that's totally equivalent to that. Okay, so does that make sense?
Yeah.
So that was part B. And then part C says, sketch 4 possible graphs where this wouldn't be the case. So there's an infinite number of graphs you could draw, but the point here is we can probably come up with 4 interesting ways, 4 unique ways for this to fail. Okay?
Fail.
Fail.
Yeah.
So what we're showing here, guys, is that the theorem, it is a theorem. Theorem means it's ironclad, it's proven. Okay? But there's certain conditions that this function has to meet in order for the theorem to hold. All right? So, and I like thinking about the car in this case, because here's one way for it to fail. I'm going to show you one way. Or maybe someone here can think of, can someone name a behavior this graph might have in this interval that would ruin the mean value theorem? That would ruin this thing?
So.
Does it have to be continuous?
Something where it's not continuous. So throw out a discontinuity.
Yeah. Asymptote.
Sure. How about an asymptote? Let's do that. So let's say here's 3. Oh, sorry, remember this one, my bad. What if I put just put an asymptote in the middle here
Love that.
and had my function? So I still have the point 36. I still have the point 7a. But what if my curve went? Notice how all of these slopes are bigger than 1/2, right?
Yep.
And then let's say the other half of the function went like this. All of these slopes are negative, so clearly this function never has, at least on this interval from 3 to 7, there is no spot where the slope is 1/2. Does that make sense?
Yep.
Okay. So the lesson here is, if your function has a vertical asymptote, you are not guaranteed to have this special point where the slope is equal to the average rate of change. All right, let's do another example. So in terms of the car, it would be, what if your car, I don't know, hits some kind of wormhole where it's going to infinity, so it goes out to the farthest reaches of the universe and then teleports back or something. That's kind of hard to describe physically, but somehow your car goes off to infinity and then comes back from infinity in the opposite direction.
It's like that Next Gen episode where the traveler takes them all the way out and then they have to get back and he like phases out of.
You know, that was a
Yeah.
great description.
Or it's like that other Star Trek episode where Q is like, I want to mess with Picard yet again, and he's just like, all right, we're going all the way to into the, I don't know, fabric of the universe at the other side.
Just for funsies.
Very
Yeah,
apt,
just
very
for fun.
apt.
Yeah.
We've all seen Star Trek: The Next Generation, so
Yes. Everyone has. Everyone
that's a good analogy. Okay.
has always. Yep. Everyone in the
So,
existence.
vertical asymptote was the first kind of discontinuity. Another discontinuity, it jumped. So do you guys notice how all of these slopes are much less than 1/2?
Yep.
Because there's your 1/2 slope. And then if you can jump, you can skip that spot where, basically this would be an easier one to explain physically. This would be in your car, you teleport it. You're driving
Yeah.
along and you just teleport. Well, okay, if you teleported, I guess your speedometer never has to hit 20 miles per hour then, because you covered that distance
You get beamed.
through magic.
You're
So
getting beamed.
you got beamed. So anyway, so a jump would also ruin it. The last two are kind of interesting. There's one more discontinuity. This one will be a discontinuity.
Is it pointy?
Oh, spoiler alert! You got the one where, because the first 3 are discontinuities, and the other one is just, you can have it be continuous, but a pointy would ruin it. So I'll show you the pointy.
Can a pointy actually be explained physically?
Not really, because you'd be basically having infinite acceleration. Bones crushed. So yeah, like if your velocity curve, if you look at velocity versus time curve, and it does this, like,
Just for
So is it like when they go to warp?
if that's truly pointy, then you're talking about an instantaneous. Well, I guess no, that would be jerk actually. Sorry, because the rate of change of acceleration would be changing instantaneously. But, yeah, if you did make this position
Yeah, that's true.
position versus time, and yeah, you're going from effectively infinite acceleration, because you're going from say 0 velocity up to some non-zero velocity with no change in time. So yeah, you'd be destroyed.
Yay! What a way to go. You know, that also happens in Star Trek. It does.
Okay,
That's
so
Actually, that's it.
3.
So I will relate this all to Star Trek from now on.
Okay, Jesse, sounds good. Okay, now the hole one is interesting because let's say there's only going to be one hole in this graph. It has to be in a very special spot. Exactly. Yes. You guys, I think you both got the idea. So take this graph basically and say the hole would have to be right there. So if there was that one special C value and you just replace that point with a hole, that would technically ruin the
Ruined. Bad day.
No.
So the way I drew this one, you'd say, okay, well, suppose this one's gonna have a spot. It's right. I can see it right around here. The tangent line would be parallel to the average rate of change. So if we just put a hole there at where the C value would have been, so that's key. That's where C would have been. Then the mean value theorem again breaks down, and then so hole, a strategically placed hole. By the way, just to throw in case this isn't clear, does a vertical asymptote say there can't be this C value? No, it just means that you're not guaranteed to have the C value if there's an asymptote. So little nuance difference there. Okay, the last one is a pointy. So what if again we went so a simple example here is kind of to reproduce this, but with a pointy instead. So what if my curve goes like that? Well, the problem here is I went from large slopes and then instantaneously changed to negative slopes, and so I never was able to get that value where the slope is equal to the average rate of change. So pointy, of course, is those are the 4 cases. Those are the 4 different cases. Okay. Thanks. Do the best. Okay. So then D is, could there be more than one C value? If so, sketch the graph. You guys probably beat me to that. I'm gonna do the same graph, but what if could there be 3 positions where the derivative? So was that question D or C? D. Okay. So could there be more than one C value? Of course. So between 3 and 7, the key is what if your curve has Humpty Dumpty, like multiple Humpty Dumpties or something on it, or wavies? So what if your graph went? I'm gonna keep mine simple like that. So yeah, there's gonna be 2 spots. So average rate of change is this. How many spots is the derivative equal to the average rate of change? Well, I can see right around here we got a spot. Okay, and then right around here there's a spot. So I'd basically have like a C1 and a C2. I'd have 2 different positions. So we're okay with that?
Yep.
I obviously could put more humps in and have as many. I could have as many spots as I wanted where the derivative equals the average rate of change. Yeah, sure. A linear function, you'd have infinitely many. You'd say for all x on the interval. It's true. That's a good mathematician's answer. It's maybe you call it a trivial example. So anyway, fun little fact here. I find this kind of hilarious that so this is established, this is a general theorem. There's a special theorem that says, for example, if these 2 values have the same exact y value, like that, try to fill in the blank here.
Then
There must be some spot where the derivative is equal to what? 0. So this dude has it named after him. It's called Rolle's theorem.
Roland Cohen.
Yeah, get rolled coal on. I just think it's a funny theorem because it's like it's like the mean value theorem, but just one specific example of it, and he gets to be famous. Like, bruh.
Yeah, bruh.
Anyway, so Rolle's theorem is
He's literally
Is-
rolling coal on.
yeah yeah. Someone's like, oh, here's this mean value theorem about how certain conditions under which the derivative there must be that would guarantee a spot where the derivative is equal to the average rate of change. He said, but wait a second, what if the average rate of change was 0? Then there'd be a spot where the derivative was 0. And maybe his colleagues were like, yes, you got it, dude. Like that is one example.
That
of
was
a
like one
theorem.
of your aha moments where everybody else is like, yes.
Yeah.
Anyway, so I don't know. Maybe he proved that before the general theorem. So I would think it's kind of funny that he has, this is obviously, it's a good flex if you're a mathematician to have your name attached to a theorem.
Heck yeah, it is.
If you're Euler, then you're like,
Yeah.
No, if only I'd aim to do that, because then everybody would have to get my name.
but that guy discovered so much stuff that he has the number not E named after him, but also just like a lot of things. So,
Yeah, the Euler method. There's so many Euler everything.
well, there's like the Euler, there's like an Euler vector if you're doing a rotating reference frame. There's that disk, that disk that I like to spin around. It's called the Euler disk. There's the Euler Toshin function. There's a lot. Trust me. There's
Yeah.
but at a certain point, you're like,
They mentioned Euler in Figures.
oh really?
Yeah, I mean that's how she like. They
Wasn't
say
that like how they
Clapper and
solved
Johnson
something?
solved the atlas.
Yeah, something about like it isn't new math, it's old math.
Yeah, how they were trying to change from a parabolic, or no, some elliptical orbit to a parabolic orbit.
It's cool.
This is one of my
Neo.
favorite movies.
I know you love that movie.
Yeah, it's-
Okay, so the last part of this question, guys, says state the mean value theorem. All right. So I'll write it for you. Lamalga. So with my accompanying diagram. So we need to generalize now. So if the interval, usually they'll say the intervals from A to B. I don't know why they chose those numbers.
Letters.
So what's the y? What do we call the y value at position A?
A1.
F of A. How about the y position at when x is B?
F of
F of-
107.
No, F of B. Okay, so then I'm going to draw a picture that kind of goes along with what I'm talking about. Okay, great. So, by the way, what is the average rate of change of this general function if it's f of b and f of a?
And it's,
There you go. F of b minus f of a, that's the rise, divided by.
Rye bread sounds really good.
Okay, I'm trying to talk you through this because if you like Google the mean value theorem, it seems very confusing when you read it. It seems like a big. Oh, remember what? This? Oh, like rise or run? Oh, okay. Oh, okay. So anyway, that's the average rate of change. So that term's going to pop up in the theorem. This term here.
Yeah.
And then we're going to say that okay, so there's going to exist. Here's my special C value. Okay. And we're going to be talking about how f prime of C is equal to that somewhere. Does that make sense?
Yes.
Just let me know if I lost you. We can rewind a bit. So we're going to make a statement, a mathematical statement about how if this function meets certain conditions, right, then there's guaranteed to be a spot where this and this are equal to each other. That make sense? Okay, so what's my condition? It's if f is continuous. That was the first thing.
Can't you just say differentiable?
We'll get there. Yeah, you could make a stronger. Well, this will be a stronger statement. So the trick is it's got to be continuous on the closed interval from A to B. But I love what you thought of that. That's great because you could certainly just skip this and say if f is differentiable from A to B, you're all set, and that'd be good. But this will actually give us slightly more functions that the theorem applies to. If we, might sound ridiculous, but if that was continuous on the closed interval, meaning including A and B, and differentiable on the open interval from A to B. So what that means is the endpoints have to be, so it's got to be continuous up to the endpoints, including the endpoints, but technically it can be pointy right there or right there, and you'd still be okay. The theorem would still apply. That's what this does. So anyway, so if f is continuous there and differentiable there, then there must exist
You gotta say.
Nothing. Keep going.
We're laughing about underlining. We're just children. It's really nice.
Keep
okay.
Continue. Don't mind us. Yeah, we just laugh about stupid things.
So this says there must exist. You guys know this symbol, I think, because we talked about this is means some C. I guess you could say a C that's between A and B, if that makes more sense to you.
Yes.
You could replace this with there must be some C in between A and B if you want, such that we're almost done. Well, here you can ask yourself if you've understood things right now, because we're almost done with the statement. What's the last thing that I'm going to write?
C is equivalent will
To
equal
the
A of
average.
B.
The average.
Yes.
Right.
Such that this is true.
Such as that is
Such
true.
that f prime of C is equal to the average rate of change.
Hey, Rob. It still looks like an animal movie.
So,
I have to actually write it.
No, I'm just doing that.
Yeah, so doesn't it mean if it's differentiable on the open A and B, that it doesn't matter if it's not continuous on those points? Because you're not actually differentiable on A and B, it's just up into A.
Yes.
sorry, say it one more time.
Okay, so if it's open A and B, like differentiable,
Mhm.
then doesn't that mean you're not actually taking the derivative at A? So
Correct,
it doesn't matter?
Meaning, well, so what you said was basically, couldn't I just lump those first two lines into saying f is differentiable from A to B? And I agree with you. The only problem with that is you'd lose some obscure functions like this. So let's say here's A and here's B. And let's say the function looked like this. Okay. Now this function is continuous on AB, but it's not differentiable on the closed interval.
That's what I'm saying. Do you need the f as continuous if you have A and B is open? Because you're not actually including the value A or B, it's just up to it.
Oh, I mean, what if you got rid of this?
Yeah. Is that
Oh, well, then your problem is, what if you have holes here? Now you're in really rough shape because this is differentiable on the open interval A to B, but
you still have a value C.
well, you don't have this anymore. You just lost this whole expression because there's no f of A and there's no f of B. So,
There's no really A or B either.
no, the numbers exist, but the function's not defined there. So the problem with this, so yeah, this is what would happen if you didn't include, like if you put these as curved brackets, then the theorem is ruined because this would become a counterexample where it doesn't. Especially hard if I do this, like you put say 2 points down. Now it's extra weird because now the average rate of change between A and B is this. Well, I guess it looks not very good. I'll have to fix it. So
Mhm.
this is a tough one. I mean, if you fully understand the necessity for this and this the first time you see it, that's pretty impressive. Most people, you got to think about it a while before it really clicks. Anyway, so I just want to pull up this page for you. So if you Google the mean value theorem and you look up like a formal statement of it, then there's Roll. Roll, my boy Roll. God, what an absolute legend. Anyway,
That's not what your tone says.
if you had read that, then you probably would have been like, "Oh, this is impossible. It's so it's so confusing." But it's within the bounds of your understanding of what you can understand. So anyway, I just want to point that out that if you go through it slowly, it actually is a pretty intuitive theorem. So let's do an example. That's just basically the intro.
No, you have much more to go through, my pupils. Young Padawan.
Well,
We were talking about Star Wars.
I'm going to do an example with you.
What about senators? The Galactic Republic.
Ooh, in my government, I'm creating my own society on anything. It's going great. I have a dictatorship going.
Just casually.
All the society is scavengers. It's really good.
That's good. That's fun. I have thought about it. I think we should do Clubhouse because it is.
Here's the thing.
I'll show you that.
Okay. I just don't want to do the slideshow.
Oh,
That's the thing that I don't want to do.
I haven't done it.
Stupid.
I haven't done it. Stupid.
If we have time, I'll go over two examples. This is 29, and then we'll look at 33 as well. So use in a calculus mindset, what kind of function is that? Okay, yeah, that's a parabola, definitely. But thinking that's our, certainly it's relevant, don't get me wrong, but okay.
Function.
Okay. I guess what I was looking for is it's continuous everywhere and it's differentiable
Oh,
everywhere.
okay.
Make sense? So what that means is if you're dealing with a polynomial, the mean value theorem will always apply, right? Because every polynomial, remember the condition for the mean value theorem to work is differentiable and continuous on that interval you're talking about. So with some little nuanced details of the closed. The thing is, that whole closed open interval thing is not really going to come up very much. It's a very detailed, very precise thing that you don't usually have to worry about. So anyway, this guy's continuous and differentiable everywhere. So what do? What do you guys think the first step is to this question? If we're looking for some C value on this interval so that the derivative is equal to the average rate of change, there's two things we got to calculate. Find the derivative.
That's
Great.
almost always a given.
Well, yeah, we are in calculus class, so it seems like finding a derivative.
That's
is
usually a pretty safe answer.
Okay, so we all agree. We got to find the derivative. What else should I find? Find the average rate of change. Okay, so the average rate of change for this function would be f of 2. So it's f of 2 minus f of 0 over 2 minus 0. So f of 2 would be 4 plus 6 plus 1. F of 0 is 1. And so, great. We're okay with that?
Yes.
Okay, so what do I do next? We're almost done.
You just set the 2x plus 3 equal to 5.
Yeah. Mean value theorem says there's going to be some C value in this interval so that this is equal to this. Okay, so let's see.
Made it so much easier. Why is it like this?
Now, it turns out parabolas are interesting. They exhibit a lot of symmetries. Not just the actual shape of them are symmetrical, but notice 1 is halfway between 0 and 2.
Yay.
Very interesting.
Whoa.
Whoa.
Crazy. That may be a broader symmetry than it appears at first. Okay, so let's do another one. Why did I jump so far forward to 33?
Sorry, I just blew Jesse's mind here.
What's the interval here? It's going from what?
2 to 5.
2 to 5.
Because it's not a polynomial.
Well, exactly. This function is not continuous on this interval, right? This function has a vertical asymptote at 3.
So do we
So
just explain?
how do we say our answer? So the way, this is an exercise in how do we give our reasoning in a way that's socially acceptable?
Oh, okay.
We live in a society.
Because of this, we're consulting.
F is not continuous on the interval from 2 to 5. You want to be really good, vertical asymptote at x equals 3 is the actual reason for that. So the mean value theorem does not apply. That's
That's
how.
gonna be the next D.
That's the standard way to write something like a justification for something like this. Okay. Now, might there be some x value between 2 and 5? It's possible, sure, yeah. Like certainly, I mean, a function could have a vertical asymptote at 3, and it could look like this. And say the average rate of change you were curious about was from here to here. Are there spots on that function where the derivative is equal to that slope? Sure, right here, right here. But were they guaranteed to exist? No. So in this case, I believe the question, if I phrased it the way I thought I phrased it, it would be something like, is there a guaranteed value? Just because I know you guys are dying to know, just because I know it.
Okay.
Let's show algebraically why I think this one's not going to happen. So the average rate of change would be plug in 5, you get 4. Plug in 2, you get -8. And then divide by 3, that's an average rate of change of 4. But the derivative would be, so 0 times that minus 1 times 8 over that squared quotient rule. Notice that quantity is always negative. So this is a function, by the way, we also know that from graphing it, right? It's a shifted whoop-de-doop-de. That's a function that always has negative slopes. But the average rate of change from 2 to 5 is positive 4. So you're never going to be able to find a value where the slope is equal to the average rate of change. So in that case, not only is your C value not guaranteed, there is no such C value. You can't find one. So at the end, they all lived happily ever after.
Is there